Yeah, I'm fine with it.
Am I audible?
Huh.
Yes, you are audible.
Okay.
Yeah, you can start.
Okay. So good evening, everyone, and yeah. So welcome everyone to the advanced talk series by Astronomy Club. Yeah, I see a lot of familiar faces in the LH. So hi from Pulkit, and we are here to take part in a wonderful talk going to be delivered by Anuja. So yeah, so she graduated from IISER Pune in 2023 with a master's in physics, and she carried out her master thesis work on formation of exoplanets, if I'm correct, which she will be talking about. Uh, from Konkoly Observatory in Budapest, and her supervisor was Dr. Ramon. Excuse me, there's a train. Sorry. So yeah, so her supervisor was Dr. Ramon Brasser, and she was also co-supervised by Dr. Shreyas Mangave from IISER Pune. So yeah, yeah. Let's just welcome her, and Anuja, you can start.
Hello. Just let me know if I should like start sharing the screen. And start with that.
Yeah, so meanwhile she's setting up her screen. I would just share that for this work she received the best thesis award in a batch, so I hope you'll be getting a lot of yeah insights into the field. Over to Anuja.
Okay, okay. Just let me know if the slides are moving on.
Yeah, they are perfect. Yeah, you can start.
So, good evening, everyone. Uh, Pulkit, thank you for the introduction and thank you, NICER Astronomy Club, to invite me for this talk. Today, I'm going to talk about my master's work. My This work is based on my master's work, but later we made it into a paper, and I'm specifically going to concentrate on the paper rather than my master's work itself. So the topic is understanding gas giant formation in our outer solar system. So we are going to talk about Jupiter, Saturn, Uranus, and Neptune, and the implications of their formation on the inner planets, that are terrestrial planets in our solar system. So I'll start with giving you an introduction, objectives, the model. It's a numerical work, so I'll give a slight model description. We'll talk about the results, implications, and conclusion. So to give an overall picture of what we are going to talk about, this is about our solar system. So how did our solar system come to be? This is a very detailed but yet very basic picture. It all began 4.6 billion years ago. A gas cloud which collapsed into a spinning disk, and there was due to nuclear fusion, our protostar, today's sun, came to be. And after the sun's formation, there was accretion and there was clumps and different materials that were still in the circumstellar disk, and these materials formed together to become planets, came together to become planets, and today we are going to talk about these very planets. So what is this protoplanetary disk that I'm talking about? On the left side of the slide, you can see a real radio image of a young Centauri disk. At the center, you can see the sun, and you can see different ring structures. And on the left, it's a cartoon of how protoplanetary disk is what we imagine to be. So there's a sun or the protostar in between, and there are different regions. There's a carbon soot line, which is basically line after which carbon starts condensing. There's a frost line, also called as the snow line, after which water starts condensing. And this basically divides the protoplanetary disk into different compositional areas. But 98% of our nebula is of hydrogen and helium and does not atoms. Please do not mistake the rings or the substructures that you're finding with these lines that I'm talking about. These are two different things. Moving ahead, we are talking about protoplanetary disk, and we are going to talk about how our planets formed in this protoplanetary disk. But every disk has a life or a timeline. And it's the timeline is divided into massive flared disk, a settled disk, photoevaporating disk, and debris disk. I'm not going to talk about detail about each component of each time frame of this protoplanetary disk, but I want you to remember that in our solar system, specifically for our sun, this particular protoplanetary disk is made of gas and dust particles. All the gas diffuses by 10 million years, and we formed debris disk is the final evolution of this protoplanetary disk with planets. So by 10 million years, we had our planets and asteroids or comets in place. Moving ahead, how does planet formation occur in circumstellar disk? This is again a very simple picture which divides our probably terrestrial planets that are the Earth, Mars, Venus, etc. from our gas giants with the snow line. And this picture is to show how different they are from each other in terms of composition. And it solely depends on how far it is from the central star. So at the end of the at the end of planet formation, we get rocky planets, asteroid belt, gas giants, and there are also at the end. So how do our planets do? We saw that there are different materials here, like the blue and the red, brown color dots, but they are not of the same size as definitely. They are from micrometer to megameter objects that are present in the protoplanetary disk. So it starts from dust, and then which are very small micrometer objects, and they go into pebbles, which are around millimeter sized objects. And these pebbles and dust together form these planetesimies, which are around meter to kilometer sized objects. These meter to kilometer sized objects start colliding and also start creating these small pebbles to form what we know as today's planets. And to form our gas giant, there is an extra process called gas accretion. So talking about planet formation, there are gas giant formation. There are two models that are widely discussed in the field. One is the accretion model, and one is the gas collapse model. I'll first talk about the gas collapse model because it is very similar to what we believe how our star came to be. There was this disk, and there was some disk instability. There was a clump of gas that got together. It coagulated to form a core, and once the core was formed, there was gas accretion. While accretion model does not completely depend on gravitational disk. It depends on the dust and pebbles that I was and the planetesimies that I discussed in the last slide, where due to non-gravitational forces these are forming, and again when gravitational forces these start accreting and form a gas once the corresponding gas is accreted from the this. So this is after the core is formed. This is how the gas grows around the planet. I'm not going to go deep into this. Once I share the slides, you can look into it. So, what is accretion that I'm talking about so far? Accretion, in general, is a radial flow of gas onto any gas or any objects onto a central object, and this is mainly driven by angular momentum transfer. And when we are talking about accretion, it's not just the gas accretion onto a planet core or the pebble or planetesimal that is accreting into onto a planet embryo. Embryos are basically a slightly bigger size objects that form that later form planets, and that's what we call embryo. And there's also, at the same point, there's also gas accretion or material accretion that is going on to central star. So when we are modeling or when we are making these models, we have to take into account all these accretion processes. So now we got to know that there's accretion, there's a protoplanetary disk. We also have our planets, and sometimes we feel that there's nothing more to know. Like accretion hota hai, and then we get our planets. But there are a lot of questions still there that we clearly don't understand, and they are widely ranged. They are from like astrochemistry, their composition, then how late accretion happened, how does this asteroid belt or the Kuiper belt come to be, why did Saturn stop accreting gas? Like it's still just 95 Earth masses, while Jupiter is around 315 Earth masses. So there are so many questions, and out of this, when I started my project, we started with two important questions. That is gas giant formation, how the formation happens, how the planet migrates, and its implications. And another important question was, why did Saturn stop accreting gas? So far, we had a lot of studies that talk about Jupiter, but we didn't really have a lot of studies that talk about Saturn. And hence, we concentrated on Saturn. But later for the paper, we went into a general gas giant formation direction. So the objectives of this project is we have a protoplanetary disk, we have gas giants, and now we want to answer three questions. That is, why did Saturn stop accreting the gas? What are the accretion models? In the accretion slide, if you remember, there was Pebble accretion and planetesimal accretion. And what are the initial conditions and disk parameters that best reproduce the formation of outer disk gas giants? So this study is basically based on n-body simulation based on Pebble accretion and planet migration. I'll explain each of this term in the coming slides. But this is basically a parametric study. Like we choose a set of parameters and see how it affects the formation of these gas giants. So what are n-body simulations? I am not going to go into the mathematical part of it. I'll just try to explain it to you in a very basic manner how it applies to my particular model. So we have the center star, okay, and then we have these blue objects that are let us call them protoplanets or MPOs for now. And then we have this gray color clouds. Let's assume they are gas, and these green color triangles are our pebbles or dust or planetesimals. And this is at time t. They are at each object here is n. Each blue object here is n that we are talking about in n-body simulations. And we have for each object defined position, velocity, and mass. Now we have in this particular system, there's a Kepler orbit that is going because it is rotating around the star. There are force calculations that take place, that force due to the central star, force to the other objects that are around it, the gravitational forces that take into account the Pebble accretion, and to envelop all this, there's this equations of motions and continuity equations that are based on our conservation laws of angular momentum and energy. So when we take into account all this, what do our simulations give? At time dt, like t plus dt, it gives for each of this object after calculating everything, the position, the velocity, and mass at dt. So here, for example, our main protoplanet has moved across the orbit. It has accreted something, so it's basically the mass has increased. And this is done for every other. I'm just showing it for one, but for every n particle, this is how the simulations work. So why did we choose pebble accretion and not planetesimal accretion can be understood from this figure. So the smallest object is the pebble, the protoplanet is the central or the protoplanet embryo. I'm going to use these terms very interchangeably. And there's a planetesimal that is around meter to kilometer sized objects. And this particular white circle that you see is called it's basically defined by the Hill area, where gravitational forces from the central objects take place, like come into force. So when these two pebbles and planetesimals are enter the Hill radii of the central object, it's easier for the pebble to get accreted onto the planet because it's very small, and because of it's very small, the mass is very small. But planetesimal, because it has a bigger size and has a higher inertia, it doesn't get accreted. Hence pebble accretion is proven to be more efficient than planetesimal accretion. And why do we need efficiency? As I talked before about the lifetime of the disk, if you remember, in our particular solar system it was around 10 million years. So before 10 million, and there was this something called as a truncated gas accretion. So if the planets moved inside 5 AU, they stopped accreting the gas, and it skewed our results, so we removed it from our results. So just to give a very quick idea about what all forces this our model takes into account, it takes into account definitely gas accretion. It has some gas turbulence. There's photo evaporation because of the central star, and there is a radial drift. And along with it, especially for pebble accretion, we have something called as a pebble formation front, which starts from near inner edge and moves across the outer edge, moves towards the outer edge. So basically, this is the orbit. Let's call it orbit, but it's not the perfect name for it. Where the pebbles start forming, and this formation of pebbles is in the outer direction. So because the pebbles are forming and moving in the outer direction, and we have this radial drift inside the towards the sun, there's a lot of collision, and it basically supports accretion. So what did we do? We divided this project into two parts. First is I talked about the Pebble accretion model. Swift Simba package is basically a solar system integration package, and Simba is the one that I use. Simba stands for Symplective Massive Body Algorithm, but I'm not going to discuss the details about the package. We looked at n-body simulations, and what we first did was look at gas disk parameters. I'm going to discuss what were these gas disk parameters, but how did we do is was we took two planets. Remember the blue objects that I showed you? So they were these were like two, or then later we went into embryo cores. So they were like 7 or 14 embryo cores in the disk, and we saw which of these cores, how these cores for different gas parameters grow into massive gas giants. If they are in between Jupiter and Saturn, in between the masses of Jupiter and Saturn, we finalize these gas disk parameters. So what are these gas disk parameters that I'm talking about? These were the diffusion time scale, that is the time that the gas requires to diffuse. There was this gas turbulence. So turbulence is one of the reasons why turbulence is one of the reasons why accretion happens in the system. So strength of accretion due to turbulence is only one of the reasons. There are different accretion parameters, but we only took one. Then in this form, what are the different coefficients that help in the formation of the gas envelope? Accretion efficiency. So when I'm talking about accretion, there are different mechanisms that take place. We only took two. One was EDA's prescription omnis. These are two different groups, and they give two different accretion mechanisms, and both of them have different efficiencies. So we tested them. Sticking efficiency is basically now the pebbles basically have to stick to the planet for the mass to increase. So it's basically sticking efficiency of the pebbles onto the planet, probabilistic parameter, mathematically speaking. And out of this, we chose, as I explained, the ones that gave us massive gas giants were the ones that are so. Moving ahead, once we got this gas disk parameters, we went into the planetesimal disk parameters. So I'll explain you what is a planetesimal disk just in the next slide. So we discussed about the planetesimal disk parameters. We run some simulations. The main statistical analysis that happened was on this, and once we got all the parameters from gas disk and the planetesimal disk, we looked into the growth time and the total evolution of the outer solar system. So the planetesimal disk that I was talking about. This is a movie, but before I start the movie, this is a planetesimal. These blue particles each are planetesimals, and this is between 5 to 25 AU. And different parameters affect this planetesimal disk. How many particles are there, and etc. That I'll discuss in the next slide. So this is how we start. As these, this is a population of planetesimals in the disk, and we let pebble accretion happen onto this planetesimals. This is how that's the basis of the next part of the study. And as you can see, by 1 million years we had our 10 earth mass cores. This is 10, so 10 earth mass cores. And by 2 million years we start forming some gas giants. And below you see that there are only few particles that are actually planetesimals that actually end up becoming gas giants, and otherwise there is a lot of instability in the system that you can see. The color coding is based on the eccentricity. So why do we get this instable like this? Why are there planetesimal scattering and all? Is one of the major implications of the study that I will discuss at the end. So I talked about gas disk parameters. So what are these planetesimal disk parameters that I'm talking about? So the accretion efficiency and sticking efficiency remain the same. The three main parameters that influence the population of these planetesimals were the number of planetesimals, the disk mass, and the initial size distribution. So all these parameters or the numbers that you can see, there was a extensive literature study that I did, and after which I had chosen what all values of these parameters should be taken into account. The number was the upper limit for this number was because of it was computationally expensive to go beyond 5K. And the size distribution actually comes from the Kuiper belt formations, Kuiper belt objects that we see today. So the size distribution comes from there. So going ahead, coming to the results part of my talk. So before I move into the results, I want to put there the planet classification. So our planet classification was solely based on mass. It was not based on the position at which these planet analogs are forming. So what we considered Saturn was between 75 to 1150. So it was basically the mass that we see currently today plus minus 20%. So these are the values that we chose for our Saturn, Jupiter, ice giant analogs, and we also tested anything that is between. So anything between ice giant and Saturn was named IS, and in between Saturn and Jupiter was named SJ. And our mean mass as well as median mass of all the simulations combined was around 135 Earth masses. So moving ahead, after so many simulations, so we had done around 840 simulations for the different parameter combinations that I talked about. And in all the simulations that we saw, I had made this kind of panels, and I did not see any panel where all the four gas giants are forming together. So as I already mentioned, do not get confused with the axis position. It is solely based on mass. So the the mass or axis, there's no correlation that if it's a 95 earth mass thing, then it will form at around 9.5 AU. That's not the case here. It is scattered around the disk. But if we are like the orange dots are Saturn, the purple dots are Jupiter, the green dots are ice giants. And we see that in this particular parameter combination, we are seeing it separately. Each panel is one particular run. So one particular system is one panel in this 15 panel graph. And we do not see Saturn or Jupiter and ice giant together in any of the panels so far. So that was one of the major results, and also something that we want to look ahead in the future. Then, as I talked about, it was basically statistical analysis. So what we did the statistical analysis was called this parameter lambda, where this lambda we just basically defined it as the total number of planets formed upon the total number of runs. And these every dot basically represents for each run how much was the planets formed. Okay, for each combination how much for the planets formed. And we ran standard KS and KS Anderson Darling tests both on the results that we got, but they did not have any statistical significance to it. So basically, what I'm trying to convey here is that our gas test parameters gave us whatever gas giants we wanted, and they were really that they were statistically significant. But later, this is only based on the planetary. These parameters are only for the planetesimal disk. So when we move ahead for planetesimal disk, we see that they do not really matter in the bigger picture. They are not like different combinations don't really give us statistically different significant output. But even though if we want to see a trend, one of the EDA's mechanism, the prescription that EDA's group give us, and the higher sticking efficiency tend to form significantly more massive planets that are basically more massive than Saturn and Jupiter. So once we were kind of disappointed of like there's no statistically significant result here, we combined everything together and we looked into the distribution of what we are getting into our simulations. So these are some CDS for axis and eccentricity. As you can see, first we look at the axis part of it. You can see these are log graphs. So it is basically constant in log. Okay, so axis. So basically, what does that mean is that there's a slight preference for these planets to form closer to the sun, but there's no mass dependence. Like for example, in our system, Jupiter, which is the most massive planet, forms the closest to the sun technically, from if you see from the outer solar system this perspective, but we did not see any mass preference there. Instead, there was Saturn and Jupiter actually formed the farthest in our systems, while the analogs that fell between Saturn and Jupiter, they formed the closest to the system. And we also saw that Jupiters have the highest eccentricity. So the red part is the Jupiter. So as you can see that others, like 80% of other analog planets have very low eccentricity, but our Jupiter's really like around 50%, 80% have a more than 0.5 eccentricity. So why was this case? We looked at one particular case. We actually looked at a lot of cases. This is one of the example case where only Jupiter is forming. So this is a time snapshot. Like you saw the movie. This is one of the cases where I just took a snapshot of the movie from 0 to 5 million years. And as you can see, at around 2.5 million years, these planetesimals that were there in the system, they start vanishing. And these planetesimals, when these start like going out of the system, either they are getting accreted or they are pushed out of the system, you see that the eccentricity of the Jupiter, this is time versus eccentricity. Eccentricity starts like dynamically becoming unstable, and finally it ends up into a very highly eccentric orbit. So why is this the case? So we believe that when there are planetesimals in the system, they when there are planetesimals in the system, they basically dampen the eccentricities of these gas giants. This is basically due to angular momentum transfer, angular momentum conservations. They themselves scatter a lot, and because of this scattering of the planetesimals that we saw even in the movie and also in the snapshot that you can see, the eccentricities of these planets lower. So when there are planetesimals that are scattering, the eccentricity is dampening. But when when the planetesimals disappear from the system, the eccentricities of the gas giants also increase. And that is also because by around 4 million years, the gas also starts diffusing. So there is no other particle in our disk that helps in eccentricity damping in the system. So our eccentricities were directly correlated with the number of planetesimals left over in the system. But why only Jupiter and not other planets? We saw that the leftover planetesimals in the system, they basically decrease with the massive planets. Like more massive the planets in the system are forming, the planetesimals are decreasing. And this was kind of also intuitive because like more massive, so more planetesimals are getting accreted into it, and hence the planetesimals are getting lower in more massive systems. Okay. So going ahead, now we will look at the time formation, or looking at the growth time distribution of these planets. So before I discuss that, I will just introduce you to the term of pebble isolation mass. What is pebble isolation mass? It's the mass after which pebble accretion stops and gas accretion starts. And that is on an average 10 earth masses found from different simulations that we did. So basically we are now assuming that the gas giants that we are forming have a 10 earth mass core. And so we saw what is the time taking for each gas giant to form this 10 earth mass cores. And from this figure that you can see that Jupiter is forming the first, like the 10 earth mass core for Jupiter is forming the first, and followed by all other giants, like followed by followed by SJ, Saturn, IS, and ice giants. And this particular graph is for one particular system. But if we compare everything, like take an average for everything and make these CDFs, we see that these time limits are actually actually exclusive. Basically, the average Jupiter formation time, 10 core 10 Earth mass core formation time is around 1.1 million years. Saturn is 3.3 and 4.9, and there is no overlap. So there are no points that are basically forming way earlier, way later. So what this suggests is that our gas giants in the solar system form sequentially, and at first thought might seem intuitive, but surprisingly there was no study before that actually showed that our gas giants in the outer solar system form sequentially. So this graph that you can see basically shows that. So it's a the x-axis is time at which our 10 Earth mass core was forming, and the y-axis is the final mass reached by that particular core. So if at 10 Earth at around 1.5 million years, a 10 Earth mass core is forming, so it will highly end up at around 200 Earth masses. So that basically shows you that giant planets form sequentially. And once we looked at the co-formation time, we also looked at the gas envelope accretion time for both Saturn and Jupiter. But here we saw that both the gas and envelope accretion takes place till 4 to 4.5 million years. This is the time till which the gas is still there, and after that it is completely diffused out of the system. So what I'm trying to say is, till the gas is there, both Saturn and Jupiter continue growing from their core masses. So what is the implication of all this? So before I discuss the implication, I want you to understand one very basic but important concept in solar system, that is called the solar system isotope dichotomy. I won't go into detail about how these things are formed, but how these graphs made. But these are isotope graphs, different isotope of same element or different elements, and basically they are seeing the abundances of these particular elements, and they are plotting this against one another. And you can see that there are two different groups. This is one red group and another is blue group. And if you see abundances of like there's oxygen, there's chromium, there's molybdenum. If you see any of these abundances, if you look at them, there are two different groups that are forming. One is the red group that is associated with non-carbonaceous chondrites, like the meteorites that we found from this region are non-carbonaceous, and another are carbonaceous chondrites. Okay, our Earth, Moon, and Mars, they basically lie in this non-carbonaceous chondrites group, while the outer solar system, or the Jupiter, Saturn, or the carbonaceous chondrite, the area from which these carbonaceous chondrites have come, they are from the outer solar system. So our Jupiter, Saturn actually belong to the outer solar system. So now, if we want to look at if our simulations are going in the right direction or not, one of the best studies is to go to like these geochronological studies and look at meteorite data. see if anything from their timeline matches with the timeline that we have gotten. So that is basically validation of our simulations. So you have gotten now an idea. So now we looked at some previous papers that looked at that basically studied this carbonaceous chondrite group. So Jupiter co-formation implication. This one thing has been taken from Kruger et al.'s paper in 2017. They had measured the accretion time or the formation time of these two groups, the non-carbonaceous group, the red group that we saw, and the carbonaceous group. Okay, and now we can see that the non-carbonaceous groups formed before 1 million years, while the carbonaceous groups formed after 2 million years. And when did our Jupiter co-form? It was around 1.1 million years. So what Kruger et al. Had suggested back then was they had just hypothesized that maybe our Jupiter is forming around 1 million years, and because the core is forming and it grows, because there, so it basically becomes a barrier so that the non-carbonaceous and the carbonaceous groups do not mix together, and hence we get the dichotomy. And our co-formation time of Jupiter basically matches their hypothesis. Secondly, Saturn co-formation implication. So there's something called as impact resetting of these meteorites. Basically, they have differentiated, but due to some high impact, their ages get reset. Um, their ages get reset, and Kruger et al. The same group had again posted a paper in 2022, which had given a particular Eagle Station parasite, which belongs to the carbonaceous solid outer solar system group, and that age was around 2.7 million years. And why does this impact happen? That time they had hypothesized that we have our Jupiter, we have our Saturn. When they are forming, they are scattering a lot of materials that is actually causing this high impact on the meteorites. As you can remember, our planetesimals were getting really scattered when our massive planets were forming. Again in 2023, like just last year, another group they remeasured all these ages with different taking different isotopes, and they again said that maybe the 2.7 million years is not quite a correct answer, like not quite a correct impact age. Maybe it is 3.76, and what we are getting for the Saturn co-formation time is around between 3.3 plus minus zero point 0.4 million years. So we believe that it basically sits very nicely in between the two ages, and this basically validates our simulations. So, summarizing the talk, I talked about N-body simulations, and I also said that we did a statistical survey on disk parameters. We saw a significant diversity in the orbital distribution of giant planets. There was no particular trend as we could see. There was sequential giant formation. The time of growth has implications on the inner solar system, because as you could see that Jupiter was kind of a barrier which did not let the outer carbonaceous contents come into it. And we could not, one of the other major results was that we could not reproduce all the four giants in one particular system. So in the future work, we definitely need to expand the parameter space so that we get all the four giants, and we want to see how the systems evolve beyond 5 million years. We want to also we what we did was a simple disk. There was no substructures as such, just the artificial trap. We want to explore more substructures. We want to investigate more mass relationships, and finally we want to explore the composition wise this study more. So I want to thank Dr. Ramon Russell and Dr. Shreyas Managave for their supervision. Dr. Sudha Rajamani has been a constant guidance throughout my IISER journey. Dr. Nina ma'am and ECS department, as well as the Concole department in Budapest to support me. So thank you. Hello.
Okay, let's thank the speaker. Yes. So, oh, okay. Please continue, ma'am.
Do you have any doubts?
I think there is some glitch. I mean,
Okay.
the Yeah, so while they are switching to the Q&A session, I just wanted to appreciate Anuja. It was a very good talk. I mean,
Thank you.
the beginning parts which we heard, like they were much better explained today than the mock. So I really appreciate that part. Thank you.
Can you share the presentation again? Yeah, 1 second. Okay, anyone in the online meeting who wants to ask questions, we are sending a contributor request. Just switch yourself to the contributor side, and then you can type in the chat or raise hand, and we can take questions from there. And we'll be taking live questions from here as well. Okay, I'll let you know, Ms. Anuja, whenever I'm muting you and unmuting you. I'll keep letting you know. Okay. You are unmuted for now.
Um, it has, is it a
Okay.
question?
Any questions, guys? Any questions? Yes. So Vasant Kashyap has a question that
Hello.
Vasant Kashyap has a question that why is the pebble formation front moving radially outwards? Shouldn't it be moving inwards due to loss of energy?
No. So, please go there. So, pebble formation front is so if the loss of energy takes place if like there are already the pebbles in the system, and because of loss of energy these pebbles are moving forward. That is there. Like the pebbles, the radial drift is also acting on the pebbles that are formed, but the formation, like where the pebbles are formed, is actually from the inner disk to the outer disk. Why did we do this is because we did so this is to save computational expense. Okay, this was solely for that. Ideally the pebbles are there in the system from the beginning, or rather the dust starts coagulating and slowly the pebbles are formed as the time is going ahead. But to model the dust accretion into pebbles, it is very computationally expensive. If we do that, what you're talking about is completely right. Due to the radial drift, because of the loss of energy, it will move inwards. But a formation then, so for that we need to include another disk, basically math, like simulation wise speaking. But just to save the time and the cost of the computation, we chose that our pebbles will form one by one in like this. Why did we choose from inner to outer? Is because our gas disk is diffusing. Okay, I don't want to go into a lot of detail into it. I just want. Uh, so the gas disk is diffusing. So there's this gas flow that is out. So the dust is flowing this way. Hence we assume like outer way. Hence we assume that with the gas flow, because the dust is also going on, a pebbles will also form that way. That was just very simple explanation why we started from inner to why did our pebble formation front and front. Was this clear?
Uh, Pulkit Bhaiya, you can ask the question. Can you unmute yourself or should I unmute you? Yeah.
Yeah, it's. I think it's possible. Yeah. So, Anuja, you were talking about the core mass while you were showing the plots in the later slide. Yeah, no need to go to the slides. I was just asking. So do we have a estimate? Do we have a way to estimate the core mass of the giant planets for our solar system or any other? I mean,
Oh,
does the core mass has any observational significance, or do we observe the entire planet?
uh, we observe the entire planet. Till date, there have been no observational kind of thing to actually see what is the exact core mass. They have always been estimates. This like because from in fact not only this study, this pebble isolation mass has been known since very long, and from different simulations or even analytical and numerical studies, they have seen that if we hit this mass, there will be like there will be no other like the gas accretion will set in. So it has been estimated that this core will be between 10 to 20 earth masses based on the composition. We have the composition of these planets, so based on the composition, and we can see how much is it coming from the gas. So there's an estimate that this much amount of these metals, for example, will be in the core. So if these many amounts of masses of metals are in the core, then how much is the mass? But there's no direct observation for the core yet. All
Okay.
are
Okay.
estimates. Yeah.
So you're saying that for the I mean numerical studies of formation of planets, the core mass is still a
Yeah,
mystery.
yeah, it has been estimated, and it has been around 10 to 20.
Okay, okay. So yeah, I have one more question. So I mean, a lot of your plots were about the eccentricity of the planet,
Yes,
and also you told that most of the current orbits in our solar system have very like almost zero
low
eccentricity.
eccentricity.
So yeah, I mean, is there any physical reason why the orbits of not just our solar system but like the more other solar systems also tend to become circular and circular? I mean, lower their
Um,
eccentricity over time.
yeah. So higher eccentricity is basically a dynamically unstable system. So what every system wants to become is a stable system, and
Oh,
stable system basically equates to low eccentricity orbits.
okay.
And
So it's an indicator of instability in the system.
yeah, it's an
Yeah.
indicator.
Oh, okay, okay. Thank you.
We have a question in the chat. If you can see that,
Can
why
you read
does
it?
yes, why does the accretion occur only in a plane? Isn't gravity acting in all directions?
That's a good question. So our disk is like it. Hmm. So there the gravity is acting in all directions, yes, but the planarity of the disk is not solely determined on the gravitational on the only the gravitational forces. There are also radial forces that are going on. There are also accretion forces that are going on. So when these radial forces are higher than the gravitational forces, the disk flattens, and that's what has happened in our particular planetary disk system. So like because of the high energy accretion that is taking place, the radiation is more than the gravitational forces. If the gravitational force were higher than this radiation force, the radial velocity forces, not radiation, sorry, radial velocity forces, then as you can we would have seen a very fat disk, and we could not have assumed it's not an actually assumption, it actually is a planar structure, but the mathematics would have gotten way more difficult if the gravitational forces were more than radial velocity forces. But in our particular system, and actually it's very commonly seen, the radial velocity forces are higher, and hence the disk flattens, and hence we can, when we are coding, we can take a planar structure. So in reality, the radius, the disk height is very low than what we see the radius. It's assumed to be like the actual h by r, and the r is very high. So the actual disk of the planet becomes like very thin, and we can approximate to it to a planar structure.
I think,
Was it clear?
yeah, I think Shweta Padma, who asked the question, she's happy with your answer. Chandan Bhaiya, you can unmute yourself and you can ask your question.
Yeah, hello. Thanks, Anuja. That was a nice talk. I have two questions. One of them is the follow-up from Pulkit's first question. Like, have you accounted for the abundance of the materials of the accretion? Like, how do you account for the densities and the availability of the material that is constantly being accreted, be it dust or gas or just pebbles?
Huh.
So, is there a density profile or something?
No. So there is no density profile in our system. We have a core to like the solid to gas ratio, but we are not particularly looking at the abundance, that because it will then come into a very geochemistry part of it. We have not taken into account geochemistry. Whatever our abundance profile will be for from the sun. Like sun has this dh ratio and everything and metallicity, and and when we are taking into account all the accretion forces and the disk formation and everything, that time the profile will be equal to the sun. But that's not necessarily the case. But we haven't additionally put any other compositional thing, like we have not added any volatiles or condensates there in the system to look at it. So currently we don't have, but that is in one of our future work that we are working on to look at the density profiles.
Okay, but how do you incorporate the like constant growth rate? Like, how does all the material come? There should be some density through the radial distance.
Oh, so there is gas density. There's a gas density profile. There is also, as I talked about, the planetesimal disk profile. Like uh, there's a size distribution of the planetesimals also. So the addition or the growth is solely dependent on the mass. So from the density at that point of time, that much gas density is there. But in simulation wise, numerical simulations wise, it's just the number that is getting added. And when we are talking about pebble accretion, that is also, I had mentioned also that these pebbles are not forming physically or not even getting accreted physically in our simulations. It's just simple mass addition or mass growth based on different calculations.
Okay, yeah, that makes sense. Okay, I have one more question. Sorry if I missed it earlier, but like, how do you classify those simulations? Like, in this, you said that Jupiter formed first, but if you see directly, even at the starting, it's just pebbles and it's just accreting. So, how do you know that Jupiter is the one which formed first and
Oh,
not any other planet?
yeah, that's also a good question. So in our simulations, we have this particle ID that gets associated to every particle. So we look at the particle, and this keeps changing. Actually, ideally, if it was not changing, it would have been very easy to track whatever was happening in that planet. But because there are mergers, like if two particles, let's say planet number 2 and planet number 8 get merged, then it will become number 2. The 8 will get pushed out, and the one that was becoming 9 became 8. So there's something called so what we did was, so we basically track the IDs. So let's say the Jupiter ends up at around 3, ID number 3 in us at the end of 5 million years, and then we have all the time outputs. Now we see that this 3 number has been there. Let's say from 5, we start from 5 and we go down, and we keep us we look we make sure that the axis and eccentricity are making sense continuously. Like it's yeah, making sense continuously, and then basically we track all these id, like the 3 can become, then later it might be 10, and sometimes it's around 1000 particle has become the third particle. So it's a very elaborate and a very time consuming process, to be honest. But we basically associate we try to see that axis and eccentricities are making sense, and these ids are making sense, and we see visually what is happening. And there's also a code that is there's a Simba analysis code that also works sometimes. It is a very it's a software that basically tracks this ID. But if you want to know how does that track the ID, this is how they track the ID. So there are different methods, but what we used was Python. But you can do it using different, like in Fortran works or that analysis software works.
That sounds computationally expensive. Yeah.
So that more than computationally expensive, it is manually very exhausting, because sometimes the computer doesn't give you the proper result. You're like, ये ID ऐसे jump कैसे किया? You don't understand it, and then you have to go back and look, and you see that, oh, it has not tracked it properly. And you have to repeat that process. Like, you really have to repeat this process again and again to make sense of what's going on and see if the particle is getting tracked properly or not accurately or not.
Sorry to interrupt you, Anuja. Chandanmaya, I think you can continue with the question. Like after the talk, there's like some people
Yeah,
here
sure.
in the room, they have questions as well. So
Sure, sure.
just
Like at what point the moons of Jupiter formed and how it is formed, and also Saturn.
can you know?
At what point in the this line the Jupiter's moons and are formed and how it is formed, as well
The
as
satellite
the
bodies.
Saturn's rings.
So he's asking like Shivadit is asking at what point did the gas giants like both Jupiter and Saturn develop their satellite bodies like moons and rings? Does it have any?
Um,
Does it have anything additional to this?
yeah. So once, so let me speak with this. So around 5 million years, let's say, they had uh, they formed the gas envelope around it. Okay, so this is how they and gas accretion happens, and then it basically stabilizes. Still, because of the hill radii, I think there are a lot of materials that are rotating around it. So now there's a separate individual system like the sun and its accreting disk. It is that gas giant and the accreting disk around it. And by in within the next 5 million years, these satellites or these things have formed. But we have to also take into account that there's planet migration going on. If you know the nice model, and if you have read about the nice model, you know that this Jupiter and Saturn, they actually came in, and then there's one of this theory that these two migrated and they went out. So when they're migrating and when they're moving around, they are definitely encountering other objects that also come into the hill radii, and then they collide and they start accrete. They don't accrete onto the planet because it's already in a stable system. So they basically rotate and clump together, get pushed out of the system, and then satellites are formed. So I would say around 10 million, 10 to 15 million years they had formed the satellite. And then I don't remember the when did that late migration happen. I'm sorry, I am not able to recall the times. So you would assume that within the next 2 million years after that event, things became stable.
Uh, just a short follow-up question from him. Is it like similar for other planets, like other ice planets or terrestrial planets as well?
Yes, yes, yes. It is similar for other planets too. But for example, gas giants are very huge, and hence they can actually have a stable satellite system around them because of their huge gravitational forces. But that because we don't see a lot of satellites, like we have only one satellite around the Earth and Moon, Venus, Mars, is because of its they are very small, so they can't have a very stable system that is going around it. But if they were large too, then yes, you would the mechanism or the physics behind it is the same.
Yeah, that's. And we have another question.
My question is that she mentioned that there is a migration trap in the simulation at 5 astronomical units. What exactly is a migration trap? And she also mentioned a lambda, which is total number of planets upon total number of suns. What was their experimental findings? Like, what was lambda?
So, your name, sorry.
Mulu.
Okay, so Mrudal has a question regarding like, can you explain the terminology migration trap, and as well as I think you showed a number lambda based on the number of planets by. So he wants you to if there is any numbers coming out of the simulations, if those numbers carry any meaning, can you explain that?
Okay, I'll first talk about the migration trap that he asked about. So, physically speaking, migration trap will be a pressure bump in the disk. So, what will this pressure bump do is when these planets are migrating towards the sun, or everything is migrating towards the sun and losing its angular momentum. So, when they are migrating towards the sun, because of this high pressure bump, they won't. Not all planets will be able to cross this 5 AU bound, and because they remain stable at this around this 5 AU boundary, there's this gas accretion that they do in the meantime. Okay, so that is how you see a migration. It's a pressure bump. So if it goes beyond it, like if it goes inside 5 AU, then there's no gas accretion taking place. Our simulation wise, like in my simulation, the gas accretion is taking only beyond 5 AU, like proper gas accretion. It stops accreting the gas once it crosses 5 AU. So between 3.5 and 5 AU, if a planet is there, it won't accrete gas. Physically it will definitely accrete gas, but not for my simulations. Okay, so why did we if so migration trap was important so that our planets that are like Jupiter, Saturn, they're all beyond 5 AU, right? So if they go inside 5 AU, and because they are very large planets, they won't stop at 3.5, or they will not be stable between 3.5 or 5. If they have already reached like let's say 115 or 120 Earth masses, right? Before reaching 5 AU. Once they cross 5 AU, they will just get lost into the sun. Like they will get basically get into the sun. So to avoid that, we decided to keep it. So first, my supervisor himself had a paper just before I started my project that talked about this pressure pump. So that was the physical explanation behind it, and like simulation wise, model wise, it was just a physical parameter after which there is no gas accretion that is taken. Is it clear now?
Yeah, it is.
And you asked about lambda. So, what are simulation outputs? Like, what it does is it gives the mass. Basically, it gives a particle ID, mass, the at at time t. For every 1,000 years, we have it, and then at t, it will give you mass, then axis, eccentricity, inclination, orbital frequency, and all those parameters that we are not talking about right now. So that is what our simulation outputs. Okay. Now for every run, we have the particle ID and the mass. From there, through coding, from there through analysis, we see that we bin these into different planet classes as I showed you, according to the bins that you can see on the screen. And once you see that, now you can count like how many Saturns are there, how many Jupiters are there, how many Icelands are there, and you know the total number of runs. So for each parameter combination, these are the 5 parameter combinations. So the gas parameters are already decided. So next, let's talk about 5. So for each parameter combination, we had 15 runs, or around 11 to 15 runs. Some runs can fail and stuff like that. So what we did for each parameter combination, what are the total number of that particular planet formed? So this is like from ice giant to total. So like ice number of ice giants formed, number of Saturns formed. So let's say the number of Saturns total formed in all the 15 runs in that particular combination is 15. Okay, let's assume the very ideal case 15, and then the total number of runs was also 15, so then lambda will become 1. That's how we have calculated lambda, but that is after like first and second level of analysis that we do. But what the simulation output is not outputs is what I explained. Is that clear?
Yeah, that's clear.
And we have a few more questions.
She mentioned that the formation of planet systems, they happen due to non-gravitational force. So, do we have any explanation for this, or do we just assume that it happens because of the disk activities?
So it's not actually because of any disturbances. It is actually because of collision. the main driving factor for these planetesimals to form is collisions, because they are not very they have definitely gravitational forces, but it is not strong enough to attract any different objects to actually come together. And instabilities form these dusts and pebbles, like these clumps, what do you say? But these clumps are again not planetesimals. These clumps actually uh, collide together to form planetesimals. So the main driving force is collisions for formation of planetesimals. And this is so there are a lot of papers that discuss about this. I can when I'm sharing this slide, I can also share my paper with which has a lot of references on this, and you can then go through these references to look at how these planetesimals are formed. People have tested different mechanisms, and then that plant main driving force behind planetesimals formation is collisions. Is that clear?
We have some more questions. If you let's see.
Sure.
Yeah.
She mentioned that the moons of the planet forming after around the planets themselves. So can we say that the rings of Saturn are an example of this same equation distance that form the moon?
Yeah.
Could you repeat?
Yeah, like you were explaining about the gas giants themselves having accretion disks on the later stage, right? So, are Saturn's rings also consequence of the same phenomenon?
Yes, yes, they are the consequence.
I am asking that is the chemical composition of pebbles best specified? And if yes, then do they show the result which we see today, which we observe, the chemical accumulation of fluid?
So, the chemical composition of the pebbles on the either side of the gas giants, the like, is it also observationally the same, like for our solar system? Like when we put in the
Either
simulation?
side of the gas giant.
Yeah, either side, the carbonaceous one and the
Oh, yeah, yeah, yeah. These. Oh, I'm sorry if it was not clear. The CO, CV, CMR. These are all meteorites. Okay, like chondrites, and they are found in meteorites. And these meteorites samples, we have these samples on all, and they have been tested. We they how do they know that they come from there? This is something that I need to read about. Thank you. That is one question. But that is so. mm, so we have this volatility thing that I talked about. It is soot line, the frost line. So there's this basic composition that happens because highly volatile elements will only condense into the outer solar system. In the outer solar system, and the inner solar system, they will just remain in gaseous compounds. So they have different this thing. So if a meteorite is coming from the outer solar system, we will accept if there's some solid in there. It's highly probable that it formed there. It can also be possible that there's some inner solar system body got pushed there. But for now, but if we have a lot of samples that are coming from there and they have similar composition, we will say that they all formed it. It's highly unlikely that all of them got pushed there. Okay. So now, if this is the composition, we now know that this particular meteorite belongs to the outer solar system. Now we see the contours in it, and we measure the different isotope abundances. And when we do that, uh, and then we can see that for different like CO, CB, CR are different types of meteorites. Okay, and even like OC and C, they are also different like there are iron meteorites, there are differentiated meteorites, there are different classes of meteorites that we talk about. So when we are sampling them, and if we every sample that they have been tested so far, they are giving this dichotomy. So all of them have different. These particular group always form in this, always land here, and this inner solar system group always land here. This is not a simulation based on anything. These are actual samples that have been studied and measured, and this is the graph that we get. Is that clear?
I was asking that have you specified those chemical composition?
Oh, okay. Wait, I think this is a kind of a modeling, but so like, did you put in the chemical compositions
No.
of the meteors in the
No.
simulation? No.
We did not. So this was the studies that I'm showing you. These are like from this slide onwards. They are from different groups, and they have tested. They are meteorite like the proper geochronology labs, and they have tested it, and they have hypothesized that this is what we are seeing is might be because of that, and from our simulations we are getting the same data that actually validates their hypothesis. So it also kind of validates our point also. Okay, maybe our simulations are going in the right direction, but we haven't actually put these compositions in the simulation. So these in numerical simulations you usually don't do that, but I guess no, so far, like you either do dynamical, like only look at how the planets are moving and stuff, and that's what we have done. And then the other part is this composition studies. So I don't think there's any group who have like mixed both of them together, but that is something that in this field it will come up in the future with more computational power. It will definitely be something like both the things will be tested together.
Okay. Yeah, I think that was a good. Uh, can I request everyone on the call to like switch on the cameras? Like we want to take a picture with everyone, and then if someone else has some questions, they can continue onwards. If that's fine with you. Everyone on the call, feel free to switch on your cameras. We'll take a picture here as well.
Should I like stop sharing the screen?
You can go to the
First
first
slide?
slide, yeah, and full screen it. I think delay.
I did not expect these many questions from Anuja, but I hope she's still enjoying.
Yeah, I hope that I'm able to clarify these questions properly.
Okay, nice.
Guys, you can come this way. We'll just take a picture and then you can stay for some
Hey,
more.
Abhinav is saying ki we are not allowed to turn on cams.
What? 1 second. I don't think so. No, you can, right? Yeah, you can turn on your cams. Try again, Abhinav. No? Did you change? Did you change the setting? Yeah. Abhinav, can you try again? Or come. Okay. I think you can try. Yeah. You can switch on your cams now. Everyone can. Save planets.
ये कब से होने लगा?
नहीं हर ऑनलाइन टॉक के लिए फोटो लेते हैं जाओ क्योंकि स्पीकर इधर नहीं है ना तो
Okay, to put in your monthly newsletter. Is it?
yes kind of
Newsletter.
That's good.
documentation management
Hi,
Vasan,
Chandan.